Hello, this is Teach Nichols. This video is on wave propagation and wave speed. In the last lecture, I talked a little bit about how media in the world are typically at a state of equilibrium. To understand what's going on with wave propagation, we need to understand what it means for a medium to be in equilibrium. Equilibrium is defined as the lowest energy state for matter. Again, everything comes back to energy. So what does a low energy state look like um, for different states of matter? Well, in a solid, because there are strong bonds between the molecules that make a crystalline shape, which is a very rigid, defined shape, the atoms at equilibrium are spaced according to what's called a minimum energy bond length. That means the protons are repelling each other, but they're attracting the electrons in the nearby molecules. And at some point, that attraction and repulsion sort of balances out, and it's the lowest energy state. That's why solids form crystals, is because this is like the happiest state um, of the two molecules that are forming up the crystal. So that's what solids look like, and it's defined as equilibrium. In a liquid, we don't have these rigid bonds between the molecules. And that means that gravity as a force is actually comparatively stronger than the forces between the molecules. And that means that the molecules are able to be pulled downwards, which is why liquids sink into the bottom of a container on Earth. The shape of a liquid is generally speaking flat. Obviously, the molecules can move around within the liquid, and they are attracted slightly to each other. That attraction is known as surface tension. It's why when you drop a droplet of water on a table, for example, it doesn't actually flatten on the table. It's got a little bit of a ball, but that surface tension force is pretty weak compared to gravity, and so liquids, generally speaking, in equilibrium sort of flat surfaces. Gases, on the other hand, have rapidly moving particles that are very far from each other. This means that there basically are no intermolecular forces. They don't notice each other at all when they're floating through the air, and there are no bonds holding the gas molecules together at all. They're going to fill the space completely. Gravity still acts on them, but their velocity or their motion means that they basically fill the container. So the particles at equilibrium for a gas are basically evenly spread everywhere in the container that they're in. So when you have a container of any kind of material and you introduce a force, the force can become a source for the wave, right? And that external force, whatever object is pushing or pulling on the medium, controls many of the features of the wave that will ultimately move through the medium. For example, the wave source controls the amount of energy in each pulse, aka the amplitude that we talked about in the previous lecture. So you can see in this EKG wave pulse map that's going on the right of this, that some of those wave pulses have higher amplitude. They were caused by a higher force exerted on the medium. The wave source controls the number of pulses and the timing of the pulses. Obviously, whenever the force hits the medium, that's when the wave is going to happen. And so that is also controlled by the wave source. The wave source also can control the shape of the wave pulses, and I'll show you some examples of this in class. But I did want you to know that waves are not always wavy, and you can see that again in the EKG that's shown on the right. Waves can be all sorts of shapes, including sawtooths and triangles and square waves. There's lots of different types of sources can result in different shapes. The last thing the wave source determines is the propagation type of the wave pulse. So depending on the direction of the wave source relative to the medium, it's going to dictate the kind of wave, whether it's longitudinal or transverse or something different as it moves through the medium. Okay, so now I want to talk a little bit more about wave propagation. Why do waves move through the medium anyway? Well, for a longitudinal wave, we know that the wave source displaces the particles parallel to the direction of the wave. This creates a pressure pulse in the medium, and those bonds are going to be stretched or compressed in the medium, transmitting the energy to the next bond, to the next bond, the next bond. A transverse wave is going to displace the individual particles perpendicular to the direction of the wave, and that creates a shear pulse in the medium, or a sliding pulse. Again, when the particle is displaced from its equilibrium position, it sort of stretches the bonds between it and the nearby particles like a spring. And then there is a restoring force that is pulling those bonds back to where they are at their lowest energy state. And that's the thing that basically flings the wave onto the next particle, onto the next particle, onto the next particle. This restoring force can be caused by, any of the forces that are keeping the medium in its equilibrium position. As I mentioned, the molecular bonds, or it could be caused by gravity. In our gas states, the restoring force is just the electric force that's actually repelling the gas molecules from each other and keeping them kind of spaced out in the medium. So whatever force keeps the particles in equilibrium is also going to be the force that basically transmits the wave energy from particle to particle to particle. A quick note that transverse waves cannot occur in liquid and gas states, and the reason is because when those particles slide in their mediums from their position, since there's no rigid bonds, they just form bonds with the new molecules that they're near. There's not actually any incentive or any pulling back to their original position. However, longitudinal waves can pass through those media. So this brings us to a really important variable, which is wave speed or velocity. While we talked about all the things that the wave source can control, the wave speed is actually controlled entirely by the properties of the medium that the wave is in. The source can't do anything to speed up or slow down the wave. The wave is going to move as fast as it's going to move in the medium. In solid media, the wave source stretches or compresses the bonds, but it's basically the restoring force in the medium that determines how fast that energy is transmitted from one bond to the next to the next. And in general, the energy transmits quickly if the medium has a very strong restoring force, right? If it's a really tight spring that's pulling back hard to try to get the medium back to equilibrium, it's going to allow that wave to travel fast through the medium. And on the flip side, if the medium is a really heavy molecule, then it actually is going to travel slower, because no matter what the force, it doesn't accelerate as much when it's pulled. There is actually an equation on the AP equation sheet that reflects the speed of a wave as it moves through a string, which is obviously a solid medium, and it looks like this. The variables in this equation are a small v that represents the velocity of a wave in a string, measured in meters every second. And the big T is tension, or the amount of sort of pull on the string, how tightly stretched the string is. And that mu is representing something known as the linear mass density of the which is the mass of a string per meter, measured in kilograms per meter. In this equation, you'll see that it's got sort of a linear-ish relationship between velocity and tension, which is what we'd expect, right? The tighter the string is, the faster the wave velocity is. And it has an inverse relationship with the mass of the string per meter. So that equation's a little bit more, funky to look at because of the square root, compared to equations we saw in ninth grade physics. But we see the same thing with the variables in the top having this linear feel and the variables in the bottom having an inverse feel. The square root is there because we have to deal with units and other things like that. But in any case, the equation is pretty straightforward other than that. In comparison, um, The wave speed in fluids, which are defined as liquids or gases together, those two states of matter comprise the branch of physics known as fluids, um, is actually not going to be able to be found using that equation from the last slide. Of course, that equation was very specific to a string, and a solid string at that. In a fluid, the wave energy isn't transferred through this strong bond stretch like a spring. Instead, the molecules actually move through the fluid and collide with molecules in other parts of the fluid. And when they collide, they exert forces during the collision, which then will cause the new molecule to accelerate and move on and hit another molecule. Since there aren't any bonds between the atoms, as I mentioned in previous slides, we can't send a sideways wave. All of the waves have to be caused by sort of linear collisions between the molecules. Here's a image showing how this sort of works. If you watch one of those little particles shown in red, you can see that it bumps against other particles, and in that process of colliding, transfers the wave energy from one side to the other. In a fluid medium, the waves are going to travel faster if the medium is hotter. And the reason they do this, if you've taken chemistry already, is that you know that hot molecules are moving faster already. It basically means the individual molecules can collide with each other more often because they're flying around in that medium faster. They also are going to allow that energy to transmit quicker if the particles are light, sort of similar to what we saw in the last equation. The lighter they are, the easier they are to accelerate. And so the force of the collision causes them to move the wave through the medium faster. Of course, on the flip side, if we have a cold or heavy medium, waves are going to move slower. This is, of course, relevant when we're talking about common waves in liquids and gases, such as sound waves, shock waves, other things like that. These trends are going to help you determine whether the wave is likely to be fast or slow in a given medium. Okay, we've reached the end of this slideshow. I've got another inspirational quote by a physicist up there for you to take a look at. Hopefully you'll take a few minutes to go back through your notes, jot down some questions, jot down some connections that you noticed, process it, highlight some things, but go through it at least one more time to make sure that you can really sink in and absorb it. Thanks for watching.